Namaskar. Today we will understand some of the characters of minerals dependent on electricity and magnetism. At first, we must understand the definition of a mineral. A mineral is a naturally occurring inorganic crystalline solid. It has an ordered internal atomic structure and it has specific physical properties that are either fixed or that vary within some defined range. Mineral has a definite chemical composition that may vary within specific limits. Some minerals exist as single elements. However, most minerals consist of a combination of several elements joined by a chemical bond to form a stable mineral compound. Elements chemically bond to one another when their atoms gain, lose, or share electrons with other elements. Now, we will look at the physical properties of minerals. Physical properties of minerals have major practical value and are very important for their diagnostics. They depend on elemental composition and the type of crystalline structure. For example, magnetism depends on the presence of magnetic minerals. Radioactive properties of minerals depend on presence of radioactive elements. The cleavage of minerals depends on features of their crystalline structure. Now, let us examine the behavior of a mineral in the presence of an electric field. When an electric field is applied on a particular material, there are three possible responses which are determined by their electrical properties. Firstly, electric current may flow freely in the material due to the presence of free charged particles in the material, that is free electrons in the case of metals, which could move easily under the influence of electric field. Such materials are called conductors. Only a small number of minerals are good conductors. They are metallic elements and the mineral graphite. Secondly, current may only flow at certain conditions when some electrons within the material receive enough energy to overcome the local binding energy. These materials are known as semiconductors. Thirdly, no current may flow within the material because there are no free charged particles within the material to conduct the current. These materials are dielectrics and are commonly known as insulators. These properties of mineral materials may be put to practical use. For example, the mineral blende, which is a bad mineral conductor, is separated from pyrite, which is a good mineral conductor. Some of the good mineral conductors are native elements, graphite, sulfides, except blende. Example of bad conductor minerals are quartz, calcite, barytes, fluor, etc. Some of the crystalline minerals exhibit unusual characteristics when subjected to stress or heating. These characteristics are piezoelectric and pyroelectric effects. Now, let us understand some aspects of piezoelectric effect. Piezoelectric effect is the creation of polarization caused by mechanical stress on dielectric minerals. Dielectric material within this capability is known as piezoelectric material. Piezoelectricity is the electric charge that accumulates in certain solid materials such as crystalline minerals, certain ceramics and biological matter such as bone, DNA and various protein in response to mechanical stress. Piezoelectricity was discovered in 1880 by French physicists Jacques and Pierre Curie. A piezoelectric mineral is one that produces an electric charge when a mechanical stress is applied, that is, the substance is squeezed or stretched. Conversely, a mechanical deformation, that is, the substance shrinks or expands when an electric field is applied. The converse piezoelectric effect can be defined as the strain on the mineral caused by the application of an external electric field. For minerals that are non-piezoelectric, the mechanical behavior and the electrical behavior are independent of each other. As for pyroelectric minerals, their electrical and mechanical behaviors are said to be coupled. In dielectric minerals, the regular repetitive arrangement of atoms, ions or molecules in a lattice is called crystal structure. The presence of piezoelectric phenomenon in minerals depends on the internal structure of the dielectric. In particular, the piezoelectric effect can only occur in crystals or minerals which do not possess a center of symmetry. Center of symmetry is a point within a crystal or a mineral with respect to which similar planes and edges are symmetrical in opposite pairs. When the mineral is elastically deformed, the center of gravity of the positive and negative charges are displaced, and the lack of symmetry prevents a net electrical cancellation. These electric dipoles leads to a macroscopic non-zero polarization field. In crystallography, there exists a total of 32 crystal classes, out of which 20 possess the piezoelectric capability. The direct piezoelectric effect was discovered when electric charges were created on mechanical stress on the surface of tourmaline crystals. The first generation of piezoelectric materials were crystals such as tourmaline and quartz. The first major practical application of piezoelectric materials came in the Great War, where it was used as resonators for ultrasound sources in sonar devices. Since then, development of the materials has led to new and better types of piezoelectric materials such as barium titanate, and recently in the field of smart structures, piezoceramics and piezopolymers. Piezoelectricity is useful in the production and detection of sound, generation of high voltages, electronic frequency generation, microbalances, and ultrafine focusing of optical assemblies. It is also the basis of a number of scientific instrumental techniques with atomic resolution, the scanning probe microscopies, and everyday uses such as ignition source for cigarette lighters. Quartz is the only common mineral in the Earth's crust that is piezoelectric. The rock granite contains about 27% quartz by volume. If majority of the quartz crystals throughout the 10-mile thick granite crust were partially aligned and cyclically and powerfully stretched and compressed, huge voltages and electric fields would rapidly build up and collapse with each half cycle. If these fields reached about 9 into 10 to the power of 6 volts per meter, electrical resistances within the granite would break down, producing sudden discharges or electric surges, which is a plasma similar to lightning. Even during some large earthquakes today, this piezoelectric effect in granite generates powerful electrical activity and hundreds of millions of volts. Tiny pieces of quartz are used in watches, clocks, and transceivers to provide a stable and precise frequency for the circuitry. Piezoelectric lighters use a spring-loaded hammer to strike a small crystal, which will produce a high voltage spark. Now let us understand some aspects of pyroelectricity. Pyroelectricity is the ability of certain minerals to generate a temporary voltage when they are heated or cooled. The change in temperature modifies the position of the atoms slightly within the crystal structure, such that polarization of the material changes. The polarization change gives rise to voltage across the crystal. If the temperature stays constant at its new value, the pyroelectric voltage gradually disappears due to leakage current. The leakage can be due to electrons moving through the crystal, ions moving through the air, current leaking through a voltmeter attached across the crystal, etc. Pyroelectric charge in minerals develop on the opposite faces of asymmetric crystals. All pyroelectric materials are also piezoelectric, the two properties being closely related. However, some piezoelectric materials have a crystal symmetry that does not allow pyroelectricity. Very small changes in temperature can produce an electrical potential due to materials pyroelectricity. Crystal structures are divided into 32 classes or point groups according to the number of rotational axes and reflection planes they exhibit that leave the crystal structure unchanged. 21 of the 32 crystal classes lack a center of symmetry, and of these 20 are piezoelectric. Of these 20 piezoelectric crystal classes, 10 of them are pyroelectric. Passive infrared sensors are often designed using pyroelectric materials, as the heat of a human or animal from a few feet away is enough to generate a difference in charge. The property of pyroelectricity is measured by the change in net polarization proportional to a change in temperature. The relationships between pyroelectricity and chemistry indicate that pyroelectric coefficients is influenced to different extents by the occupancy of the X, Y and Z cations. Examples of pyroelectric minerals are tourmaline and topaz. Tourmaline is a group of minerals displaying the widest variety of gemstone colors in the mineral kingdom. Tourmaline is a pyroelectric mineral, meaning that when warmed, it attracts dust and other lightweight particles. Differently colored tourmalines exhibit different degrees of pyroelectricity. For example, black varieties are the weakest, whereas rose-colored tourmalines are most strongly pyroelectric. This property has important electronic and industrial applications. The field of pyroelectricity flourished in the 20th century with many applications, particularly in infrared detection and thermal imaging. Pyroelectric sensors have been carried on many space missions and have contributed significantly to our knowledge of astronomy. Now, we examine the properties of minerals related to magnetism. Several minerals react when placed within a magnetic field. Some minerals are strongly attracted to the magnet, others are weakly attracted, and one mineral is actually repelled. There are also several minerals that are attracted to magnetic fields only when heated. Based on the magnetic properties, minerals can be classified as follows. Number 1, ferromagnetic, which describes strong attraction of minerals to magnetic fields. This property is exhibited in a few minerals, notably magnetite and pyrrhotite. Number 2, paramagnetic, which is the weak attraction of minerals to magnetic fields. The attraction is usually apparent, but it may be so weak that it is undetectable. Most paramagnetic minerals like iron sulfides and oxides become strongly magnetic when heated. A small number of paramagnetic minerals such as platinum are not essentially paramagnetic, but contain iron impurities which are responsible for the paramagnetism. However, some specimens that are not paramagnetic and lacking iron also exist, like hematite and franklinite. Number 3, diamagnetic minerals refers to repulsion from magnetic fields. Example, bismuth. Only a variety of one mineral acts as a magnet, generating magnetic field on its own. This mineral is lodestone, the magnetic variety of magnetite, which is found in only a few deposits throughout the world. Although it is only weakly magnetic, its magnetism is definitely discernible. Many of the most important magnetic minerals on the earth are oxides of iron and titanium. Most minerals with no iron content are diamagnetic. Most iron-bearing carbonates and silicates are paramagnetic at all temperatures. Some sulfides are paramagnetic, but some are strongly magnetic. Permanent magnetism is caused by the alignment of magnetic moments, and induced magnetism is created when disordered magnetic moments are forced to align in an apparent magnetic field. Curie temperature or Curie point is the temperature where a material's permanent magnetism changes to induced magnetism. Magnetic susceptibility refers to the degree of magnetism of a material in response to an applied magnetic field. In rocks, magnetic susceptibility depends on chemical or mineralogical composition of the rocks and on later metamorphic processes and alterations. Very important controlling factors are also the fugacities of oxygen and sulfur. Magnetic susceptibility provides us with invaluable information in this respect. Difference in chemistry plays a significant role in the extraction of end members of a mineral series in which iron replaces magnesium, as in olivine series. For example, forsterite, the magnesium rich end member, is extracted in the range of 0.4 to 1.2 amps, and phyalite, the iron rich end member, is extracted in the range from 0.1 to 0.6 amperes. As an example of different magnetic properties for minerals with similar compositions is the difference between pyrite, which is FeS2, and pyrrhotite, which is Fe5S6 to Fe16S17, which is ferromagnetic. These two minerals have distinctly different physical properties due to the atomic structure. Magnetic susceptibility is probably the most easily measurable petrophysical parameter. It can be measured not only in the laboratory on rock specimens, but also in the field on rock outcrops. Various instruments for measurement of magnetic susceptibility in the field on rock outcrops have been developed recently. Magnetic susceptibility of rocks is in principle controlled by the type and amount of magnetic minerals contained in a rock. Sometimes it is dominantly controlled by paramagnetic minerals, often by ferromagnetic minerals, and much less frequently by diamagnetic minerals. As the ferromagnetic minerals mostly belong to accessory minerals that are often sensitive indicators of geological processes, the magnetic susceptibility is a useful parameter in solving some petrological problems. In many minerals, the magnetic susceptibilities are not single values, but rather wide susceptibility intervals. This reflects variability of susceptibility with chemical composition of the minerals. For example, in orthopyroxene, the susceptibility is very low in the members free of iron, while in the member which contains no magnesium, it is relatively high. In general, the magnetic susceptibility in minerals depends on the ratio of magnesium to iron components. In titanomagnetites, the susceptibility depends on the amount of titanium in the mineral, and generally it decreases with increasing titanium content. Magnetic susceptibility of granitic rocks is very variable, ranging in the order of 10 to the power of -6 in leucocratic granites to the order of 10 to the power of -2 in some granodiorites or tonalites. Volcanic rocks, particularly the young ones called neovolcanics, are often strongly magnetic, and variation in magnetic susceptibility can be an important geological indicator. For example, the original titanomagnetites, being the carriers of magnetism in these rocks, can disintegrate or change in structure and or composition during low temperature oxidation or other changes. Magnetic susceptibility of sedimentary rocks is in general very low. Now we discuss as to why we have to measure magnetic susceptibility of rock outcrops in the field. Magnetic susceptibility cannot be assessed on the basis of external appearance of a rock under interest, even though the mafic rocks show in general higher susceptibility than felsic rocks. There are many examples of light granites being both weakly and strongly magnetic. On the other hand, some dark rocks like gabbros and lamprophyres can be weakly magnetic. Another aspect of magnetism related to minerals and rocks is remnant magnetism. Remnant magnetism left behind in a ferromagnetic material such as iron after an external magnetic field is removed. It is also the measure of that magnetization. Natural remnant magnetism, NRM for short, is the permanent magnetism of a rock or a sediment. In some forms, it can preserve a record of the Earth's magnetic field and the tectonic movement of the rocks over millions of years. Natural remnant magnetism forms the basis of paleomagnetism and magnetostratigraphy. Paleomagnetism is the study of the record of the Earth's magnetic field in rocks, clays or bricks. Certain minerals in rocks lock in a record of the direction and intensity of the magnetic field when they form. This record provides information on the past behavior of Earth's magnetic field and the past location of tectonic plates. The record of geomagnetic reversals preserved in volcanic and sedimentary rock sequences, that is magnetostratigraphy, provides a time scale that is used as a geochronological tool. Magnetostratigraphy is a geophysical correlation technique used to date sedimentary and volcanic sequences. The method works by collecting oriented samples at measured intervals throughout the section. The different types of natural remnant magnetism in rocks are thermoremnant magnetism, chemical remnant magnetism, and depositional remnant magnetism. We will understand some aspects of thermoremnant magnetism. Thermoremnant magnetism, or TRM, is acquired during cooling of rocks through the Curie temperature of magnetic minerals and is best source of information on the past Earth's field. This form of magnetization is generally the most important because it is stable and widespread, occurring in igneous and sedimentary rocks. Now, some aspects of chemical remnant magnetism. Chemical remnant magnetism, or CRM for short, is the magnetization formed by phase change, chemical action, or growth of crystals at low temperature. It is particularly important in some sediments and metamorphic rocks, which typically takes place at constant temperature in the Earth's magnetic field. Now, we pass on to depositional remnant magnetism. The depositional remnant magnetism, or DRM for short, is the magnetization of sediments acquired during their formation or a post-depositional remnant magnetization afterwards. It is formed in clastic sediments when fine particles are deposited on the floor of a body of water. Marine sediments, lake sediments, and some clays can acquire DRM. The Earth's magnetic field aligns the grains, yielding a preferred direction of magnetization. Many samples have more than one kind of natural remnant magnetism that are superimposed. A rock may be regarded as a heterogeneous assemblage of minerals. The matrix minerals are mainly silicates or carbonates, which are diamagnetic in character. Interspersed in this matrix is a lesser quantity of secondary minerals, such as the clay minerals, that have paramagnetic properties. The weak and variable concentration of ferromagnetic minerals plays a key role in determining the magnetic properties of the rock. The most important factors influencing rock magnetism are the type of ferromagnetic mineral, its grain size, and the manner in which it acquires a remnant magnetism. A remnant magnetism acquired at or close to the time of formation of the rock is called primary magnetization, whereas a remnant magnetism acquired at a later time is called secondary magnetization. Examples of primary remnant magnetism are thermoremnant magnetization, which an igneous rock acquires during cooling, and the remnant magnetizations acquired by a sediment during or soon after deposition. Secondary remnant magnetism may be caused by chemical changes of the rock during diagenesis or weathering. Apparent polar wandering paths provided the first clear geophysical evidence for continental drift, while marine magnetic anomalies did the same for sea floor spreading. Paleomagnetism continues to extend the history of plate tectonics back in time and are applied to the movement of continental fragments or terrains. Now, we will look at the applications of rock magnetism. One major application of rock magnetism is to measure the movements of rocks since they were magnetized, which can be due to plate tectonics or tectonic tilting. Another application is to measure the thermal history of a rock, such as reheating or temperature of emplacement of a pyroclastic deposit. Successful applications require an understanding of the magnetic field of the Earth and how rocks became magnetized, and detecting whether this magnetization has changed subsequently. Mineral magnetism utilizes the variation of the magnetic properties of rocks to study processes such as erosion and deposition. Magnetic fabric is when magnetic properties vary with direction in a rock, which is used to deduce fluid flow when the rock formed or subsequent deformation. The Earth's magnetic field, present and past, can be deciphered. Paleomagnetic poles of southern continents are incompatible with their present day arrangement. They agree better when the continents are rearranged in a Gondwana cluster. Paleomagnetism, dealing with secular variations of the Earth's magnetic field, indicates slow and irregular variations in the Earth's magnetic field. Inversion of Earth's magnetic field occurred at regular intervals. Paleomagnetic studies have demonstrated continued drifts and seafloor spreading.